You know how you can get energy. You can eat, sleep, but what exactly is energy? Well, energy is one of the most useful and unbelievable concepts in all of physics. Where's the energy, man? We need more energy. Here. Have this. Woo!
Blue Cow, the energy for work.
From our daily experiences, it feels like energy is this enigmatic and volatile substance present in us all in different and ever-changing amounts. When we feel energetic, we feel capable of doing a lot of stuff, of doing a lot of work. But is energy really this weird, palpable, jelly-like substance that we can sip from a can? Let's find out.
Energy is a far-reaching and powerful idea. In physics, energy is merely a number. It's an abstract property that objects and systems can have. But what is this number exactly? What is energy? Well, to answer this question, we have to first understand what this question means. Imagine a car. This car, right now, has a precise place in the universe, and we can label where it is using a property called position. If the car then starts moving, we can label its motion using a property called velocity. The motion of this car is definitely real. We can see it. Look, it's moving. But the velocity that we have labeled its motion with is not a real thing. It's just a human-made number. This number that we've assigned to it gives us an idea of the motion of the car. It helps us measure it. Right now, the motion of the car is uniform. It's traveling with uniform velocity. But if we were to press on the accelerator, the velocity of the car would increase. And we measure this change in velocity of the car using another numerical property, acceleration. And from Newton's laws, we may establish that this acceleration was caused due to yet another property, force. These assigned properties measure some specific parameters. So, what about energy? The question, what is energy, is basically asking, what does energy measure? The widespread academic definition of energy is that it's the ability to do work. This seems quite intuitive. When you feel energetic, you can do work. But here we are not referring to any kind of work. Work here is what happens when an applied force causes an object to be displaced. Say that I push a broken down car down the road with a constant force of 100 newtons. The car moves forward by a respectable 10 meters. Here the physicist would say the car had work done on it. I pushed the car with a constant force of 100 newtons over a distance of 10 meters. If I take the constant force applied and multiply it with the displacement of the car, 100 newtons and 10 meters, I get the total work done on the car, 1000 Newton meters. The unit used for work is the joule. I did 1000 joules of work. For us to say that work has been done on a system, the force applied on it should have contributed to the movement of it. If in the place of the car, we consider a truck as our system, I cannot push it forward through applying a force, even if I drink 10 cans. Therefore, since displacement is zero, the work done is zero. If I ask Spider-Man to pull the truck forward, he can do it. He can do work on it. There is one thing to note though. Spider-Man had webs. He's cheating. That's why he could move the truck. It's that in both cases, the direction of the applied force was different. When I pushed the car, the direction of my applied force was exactly the same as the direction of the motion of the car, parallel to the ground. However, when Spidey pulled on the truck, his hands were at a higher level than the truck headlights on which he stuck his webs. The motion of the truck was parallel to the ground, but the force was not. Since the force was at an angle theta of 45 degrees, not all of his force contributed to the motion of the truck. But when calculating the work done on it, we only consider the force that did contribute to the motion. So, to find Spidey's force that moved the truck forward, we have to divide the force into its component parts, the parallel and perpendicular parts. The parallel component was what moved the truck parallel to the ground, and we can find it using cosine. The parallel component of the force is 707 newtons, and the displacement of the truck was 10 meters. Hence, the work done on the truck is equal to 7,071 joules. Alright, big deal. Spider-Man did more work than me. So, for work to be done, the system should have moved, and only the component of the force that contributes to said movement is considered when calculating the work done. When work is done, stuff happens. As we saw here, stuff happened. The two vehicles moved in their respective systems because work was done on them. Technically then, work is a measure of how much stuff has happened, right? Yes. Work is a measure of the amount of stuff that has happened or the amount of stuff that will happen. This all began from the definition that energy is the ability to do work. And if work is a measure of the amount of stuff that has or will happen, then energy is a measure of the amount of stuff that could happen. Energy and work are just properties, numerical properties. They're numbers, just like velocity, acceleration, force. However, unlike velocity, acceleration, and force, energy is hidden from view. Energy is only calculated on the basis of other properties of objects. And there are a wide range of properties, as there are a whole lot of different forms of energy that we know of. We're cruising down the highway in our car at a constant velocity of 90 kilometers per hour, or 25 meters per second, due east. We can assign this car a certain value for energy. This type of energy is called kinetic energy, the energy associated with motion. Since energy is a property, we say that this car has kinetic energy. We calculate the exact value for energy using this equation. Energy equals half mv squared. The car has a mass of 1000 kilograms and a velocity of 25 meters per second. Based on that, we calculate that the car has a kinetic energy of 312,500 joules. Yes, energy, just like work, is also measured in joules. Work is a change in energy. The equation we are depending on to calculate the kinetic energy of this car, half mv squared, is not arbitrary. It's been carefully crafted and can allow us to make predictions about our system if something were to occur. The formula for kinetic energy can be derived by using F equals ma, this kinematic equation, and the aforementioned formula, work equals force times displacement. The above equation is called the work energy theorem. The work energy theorem tells us that the work done on a system is equal to the change in kinetic energy of the system. The first ever rudimentary mathematical formulation of kinetic energy came several hundred years ago from the German mathematician and philosopher Gottfried Wilhelm Leibniz. Leibniz was a famous contemporary and rival of our beloved Sir Isaac Newton. The two had many feuds and made immeasurable contributions to science and mathematics. Leibniz empirically established that the sum of mass times velocity squared for a system of particles bouncing around on a flat surface is conserved. Imagine we have a pool table with 5 balls bouncing around all over the place. Let's ignore the friction between the balls and the table. Because they are constantly colliding with the walls of the table and with one another, the individual velocities of each ball is ever changing. However, even still, if we were to examine this system at any instant, the sum of the masses of each ball multiplied by their specific velocity squared at that instant would be equal to a constant. This is what Leibniz learned, and he called this insight vis viva, the living force, not to be confused with vis mortua, the dead force. Meanwhile, Newton was working on his idea of conservation of momentum, which may also apply to this system, even if we do not omit friction and air resistance, unlike vis viva. Vis viva was a premature version of the idea of the conservation of kinetic energy. Just like how we learned that momentum is always conserved, kinetic energy is also always conserved. But we did not always know this. Only 7 years after it was first contrived was vis viva proven to be conserved, just like momentum. And it was done so by the 18th century philosopher Émile du Châtelet. Kinetic energy is one generic type of energy. There are others. One is potential energy. What is potential energy? Potential energy is the energy associated with position. More specifically, the position of an object in a field, such as a gravitational field, for example. This type of energy, potential energy, is called gravitational potential energy. And on Earth, it's basically the energy that exists because of gravity. This form of energy was evoked, among others, by du Châtelet. Say I pick up this football from the ground. I raise it by 1 meter. It has just gained some gravitational potential energy. If I drop the ball, it will fall. It will do something. It will do stuff. The ball will accelerate downward. The height from which the ball is dropped is directly proportional to the potential energy of the ball. To calculate precisely the potential energy this ball has, we must do two things. First, we have to measure a distance from some reference location. And then we have to plug our values into the equation for the gravitational potential energy. Gravitational potential energy equals mgh. Our reference location, in this case, will be the surface of the Earth. And so the height of the ball will be 1 meter. The mass of the ball is 0.5 kilograms. And the acceleration due to gravity here on Earth is equal to 9.81 meters per second squared. Plugging in the values, we get that the potential energy of the ball due to Earth's gravity is equal to 4.905 joules. So, we've calculated the energies of the ball and car, and we know that these are just ascribed numbers, numerical properties. But does this notion imply that we can ascribe any random number to a system and call it its energy? No. The energy values we've allocated are based on some very, very precise mathematics. The reason for this is that everything around us behaves in such a way that the total energy of a closed system remains constant with time. This leads us to one of the most powerful tools in science, the law of conservation of energy. The law of conservation of energy states that energy cannot be created nor destroyed. It can only be converted from one form to another and transferred between objects. Hi, thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I've also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.